Welcome back, 4061ers. This will be a video to make up for the lecture we missed on account of weather, in which we begin our discussion of processes. We started this discussion a few days ago, and the reading material associated with it comes out of Stevenson and Rago, Chapter 7, and quickly we'll move into Chapter 8 early next week, where we actually start creating processes using the fork command. But for the moment, we're going to take a high-level view of this. We've already discussed briefly that processes that are running, and these are programs that have been initiated by the operating system and are actually doing useful work, hopefully. They have a number of states that they can be in. On creation, they're in a new state, and after that startup is complete, they're put into the ready queue, and the operating system scheduler may at some point elect to move them to the running position, in which they'll actually have the CPU and be able to execute instructions associated with the program. Now, there's a time limit set on that, and usually some hardware support that will cause context to switch back to the operating system, which, if on seeing that quantum expired, will move that process back to the ready state and probably select a different process to run. This continues until one of two things happens. Either while running, the program reaches termination and asks the operating system to close it down, or move to the done, and eventually the operating system will clear it out and recoup the resources it used. Or alternatively, the process could make some requests, such as an I/O request, which will require the operating system to do things on its behalf and perhaps interact with hardware that will take some time. The process needs whatever information is coming in, for instance, from I/O to proceed, so will remain in this blocked state. The operating system will occasionally check on the resources that are associated with this request, and when that completes, will move the process back into the ready position, but otherwise it won't get scheduled to run until it moves out of this block state. Now, this is sort of standard operation. There are a bunch of other things that can happen that we'll look at later on during this discussion. But for the moment, you should keep this picture in mind. Another set of sort of statuses associated with processes that you're actually able to view, as in this state transition diagram is mainly internal. These state of a process can actually be viewed using commands such as PS, which shows the state of processes, or at least a snapshot of it, and the top command, which is extremely useful for looking at what is gobbling up resources such as CPU on a running system. Now, these tend to present some column of information that we'll look at in a second that either has an S or a stat mentioned for that column, and then a single character representing the state that a process could be in. Running may be either it's actually occupying the CPU or it's in a runnable state. And it's not necessarily the case that the operating system will, in these top and PS programs, distinguish between those two, which is somewhat interesting. There's an S state, which corresponds to suspension or interruptible sleep, as in the process is on hold for the moment. It doesn't need to do anything, so has requested to be woken up after some time. There's also an alternative to this in that the operating system can elect to stop a process, in which case it won't restart until it is received some signal that it's okay to proceed. And the final one that's most common to see is a zombie process, something we'll talk about a little bit later. Slightly less common things to observe in PS or top are the D state, which corresponds to an uninterruptible sleep, paging via the W, and X, which ostensibly you should never see if things are going right on your system. So a few notes on that. Top is an interactive program, and it's worthwhile just to have a look at what's going on with it. I'm going to bop over to a terminal over here and request a run of top, and you'll see my configuration for this has up top the CPU meter associated with the 4 cores that I have on my machine, and then down here is what you'll almost always see, which is a listing of the processes that are presently running. You'll see this guy up here, OBS, that's occupying quite a bit of CPU right now, and that's on account of it's the video recording software that I'm using right now to convey this to you. Other things that you'll see along here running or in partial sleep, there was top sort of flashing around. Xorg is responsible for providing graphical display on a lot of Unix systems. Chromium, my browser. Pulse Audio, which is part of the audio subsystem in Linux. So a lot of different things bopping around in here. Top is interactive, and you can do lots of different things to sort of filter. For instance, some of my favorite, the default ordering here is based on CPU utilization. I think it's the capital M command will alternate to show top memory users. So now this is sorted by the memory column, and you can see that Chromium is using some amount. The Cinnamon desktop is using some amount of memory, but the amount of memory used by each of these programs is ascending as you go along. As with many interactive programs like this, something like a keystroke of Q will quit to get you back to the prompt. The other one that's worth knowing about is the PS command, which shows you not an interactive, but instead a snapshot of running processes. I type PS here, and by default, it will just show me the processes associated with this terminal while that's running. In that case, it's the PS command that I just launched, and bash the command shell that is sort of running within this terminal. You want a little bit more use or sort of information for that, you can use a PSU, which will show you all of your user processes. And these, you can see on the left-hand side, displays changed a little bit to show my user information, along with a snapshot of what top would show me interactively, how much CPU, what the status or state of the process is, when it was started, and how much CPU time it's used, and the command that's associated with it. This can get rather long, so you may want to pipe this into a pager, or at least fire it up in a terminal that allows you some scrolling. If you want to see instead all processes, I believe that's capital A. So maybe it's just A. Yeah. In which case, some of the ones that are actually, these all look at that. Maybe it's dash A. Yeah, I think this will be then all processes that are on there, including stuff that doesn't belong to me. For instance, the network manager, which is part of the operating system running, making sure that I have wireless on go. So to that end, PS is one of the oldest sort of programs that exists and has persisted in Unix, so has a tremendous number of options and styles that you can use to show information. We'll explore one of them briefly in just a second. PS is non-interactive, so you get that snapshot. No need to know any other sort of commands associated with it. But I'd like to talk just briefly about observing processes, which can be kind of painful. It's possible to do in top with the right set of commands, but use of PS and another command, watch, are useful for this. Watch is a command that will repeatedly run some other command at intervals. For instance, in this case, it will run it every 0.1 seconds, and with the right options to PS, we can actually observe an individual process at work. So let me bop over here and get both these terminals open at the same time. I'm going to run the command yes over here. Actually, well, let me part this. So there's watch. I want to repeatedly run something. There's a every 0.1 seconds I want to run it. I want to show this in user sort of mode so that I can see some interesting information, such as the process data. I want to restrict the command to the yes command. That's what run. Now, as I run this, the screen will change to show the results of running that PS command, and you can see there's nothing listed here right now because there are no yes commands running. Yes is a really simple command that will just repeatedly spit back some character or characters that are on the screen. You can see this terminal is just flying by right now. And I'm starting to run that. The watch, which is running PS every 0.1 seconds, it actually picks up on the fact that now there is a yes command running someplace there. You can see this thing toggling between an R and an S over and over and over again. That's because yes takes a little bit of time to actually put something on the screen, in which case it'll be in the sleep state, and then flips back to the runnable state when that's happened. It's using about half or so of a CPU, and if this seems semi-impressive to repeatedly put yes on the Y on the screen here, then know that we'll actually be able to get quite a bit more performance out of this in a second if we can remove the need for it to be in this sleep state. And all of that has to do with terminal communication. I'm going to actually press a Control-C over here, sends the interrupt signal, gets rid of my yes, and ask instead about the GNOME terminal, which is the terminal emulator that I'm running here to do that stuff. I guess that's not it. GNOME term? Maybe? Nope. How about just GNOME stuff? Let's see. I'll fire up top and ask Oh, it's probably something a little bigger, so it's gnome terminal something or other. I'll move that back over here. Gnome terminal, interesting. Just gnome terminal. Still nothing. Okay, well, suffice to say for the moment, a lot of the hang-up on yes has to do with the fact that it has to actually talk to the terminal to get characters displayed on the screen. I'm going to, over here in the left-hand terminal, press Control-C to end that process, and you can see it pops off. If I, instead of having this print to the screen, put the output someplace else. And a common place, if you don't want to fill up your desk, is dev/null. That will write to a special file where output is just ignored. We'll talk more about output redirection in the future. I've run this command and nothing will come onto the screen, but you can see that there's a lot more CPU utilization and no switching back and forth between the runnable and sleep state for yes, because it takes almost no interaction with the terminal and no interaction with the operating system to write to this file because it's essentially ignoring what's in there, so there's no lag as it writes stuff. So this will stay in the runnable state almost continuously and occupy quite a bit more CPU. This is a sign that I/O is a relatively expensive request to the operating system, which can take some lag time, and trying to avoid it, or at least write not to a slow device like a terminal and instead write into a file, will occupy quite a bit more time. I'm going to kill this thing for the moment. The last thing you might want to try on this, and be very careful as you do this, I'm going to write this into a file, XYZ. Similarly so, I'll get quite a bit of CPU utilization here. I'm going to kill that quick. You can see the bar ticking up pretty fast there, but not quite as high as the null, because that kind of I/O actually writes to a file in my home directory under the temp directory XYZ. And though it's faster than writing to the screen, it's not as fast as output that's going to be discarded. Now, in that brief run of writing Y's, you will see that I actually wrote quite a bit of stuff there. So if I look at the DU, disk utilization, of the file mentioned, that's that XYZ guy, I wrote 2.2 gigs in that brief interstice, which gives you an idea of how fast things can be written to a reasonably fast disk in ideal circumstances. Now, that's certainly not something I want sitting around and clogging up my hard drive, so I'm going to remove it immediately. And you can see that took a brief moment, but this gives you sort of an idea then that I/O can be fast, not quite as fast as discarding output, but certainly way faster than writing to the screen. So I'm going to issue Control-C over here to get rid of that watch and return to our slide deck here. So interesting tricks that you can see then, and this is a reminder that you can see the states that are listed up here that are and S, as we've seen. We'll see some more of these as we progress through the lecture. A common trick associated with terminals that is useful and relates to the sort of process state is to be able to issue commands and then potentially suspend them or recall them back into the foreground. This is offered by most terminal emulators, the canonical shell, as it were. So I'm going to jump back over here, type that yes command again, which is going to put things on the screen. The keystroke Control-Z will suspend that process. It hasn't been killed, it's still sitting around, and I can see within this terminal which jobs are available for resumption by asking what jobs are there. And you can see here number one is this yes guy. If I type in yes and I let's see, I'll type C this time. The command argument here, C, will change what yes prints repeatedly, so you can see repeatedly C here. Press Control-Z again and ask for jobs. And you see I've actually got two sort of suspended in the background right now. Now, if I bop back over here to my watch guy and fire that back up, you can see two yeses here, and they're in the state T, which is they've been suspended. They will not be rescheduled to run again unless I actually issue a command that's associated with resuming them. Now, I have no idea right now why they're occupying CPU, but this isn't a really big concern. If I, for a moment, actually suspend this. I'll just kill this guy and look at top. It should be the case that there are no yeses up here, as in they're not actually occupying any CPU or any appreciable amount of CPU. Versus if I bring this back into the foreground, which is the FG command in most terminals, I'll bring number 1. And the percent here refers to the jobs here. It'll substitute the process ID in many cases for this. So this should start putting Y's back on the screen. And you can see GNOME terminal ticks up again. And with respect to that, I'll suspend this guy for a moment, ask about jobs again, and I can actually bring number 2 back up, which will start bringing C's back onto it. And you can see then GNOME terminal and yes start to occupy more CPU. Associated with job control then, in addition to bringing something back into the foreground, is you can put things into the background. Now this is going to get a little wonky because if I put this into the background, I'll be able to type things on the terminal, but there's all kinds of stuff that's going to fly onto the screen in addition, since I'm sharing both the output of this terminal, the command is also putting output onto the screen, so it makes it a little bit sort of tedious in that respect. So I'm not actually going to do that right now. Instead, what I can do is, for instance, to open up an editor and suspend it. Common example of that, if I wanted to edit some program, for instance, in here there's, let's see, bad memory that we'll look at later on. I can say bad memory along those lines, and this will fire up the VI editor. If I press Control Z at this point, that will suspend VI, and in terms of jobs, I have 3 now. If I wanted to resume VI, it's the most recently run one, so I can just say foreground, which will bring it back, or I can issue the job number 3 to bring it back, suspend it again. This is much more common and leads to faster startup than repeatedly starting VI and then quitting it and then starting it again. It's a fast startup editor, but it's always faster to suspend something and resume it than it is to completely shut down. So to that end, if I wanted to bring back the C, that would be number 2. I can suspend it again, and then tied up in that, the kill command will understand, for instance, here's number 2, and I actually want to get rid of this thing and bring back my watch for this. As I would kill this thing, you'll see that C guy go away and report from the terminal that it has terminated something. So this basic job control stuff can allow you to get quite a bit of work done in the terminal. For instance, right now I've got VI running on bad memory. I could also VI on overflow.c and suspend this. Now I've got a couple VI sessions. I can resume either of them at will to bring them back into the foreground, and they'll just sit there waiting for me until I actually would either kill them or bring them back into the foreground. So basic job control is pretty useful in that respect, and the FG and BG commands then are potentially useful along those lines. The last bit we should talk about is to automatically launch a process in the background. Now this is appending an ampersand at the end of some sort of command. So for instance, launching an ls here will list the files that are in this directory. Launching an ls with an ampersand will launch it in the background, but since it's complete so fast, I can barely see any difference along those lines. Instead, I could, for instance, launch yes, and that will pipe that into a dev/null. And at this point, that process is going to run forever. You can look over here. It's occupying a tremendous amount of CPU because all of that output it's producing is being ignored. I could, for instance, press Control Z to suspend it. That will put it into the T state, and then BG it. It's the most recently run process, so that'll go into the background, and it starts running again. It's backgrounded now, and will continue running without intervention until, for instance, I killed it. Kill it with something along these lines. There's a kill. Nope, sorry, that's foreground it. See, so I'll background it again, and what I want to do is kill it this time. So there's a kill 5, and it goes away, and we've lost one of the yeses in there. Now, if you immediately want to put something into the background, for instance, here's that yes command, as in it's going to be long running. It's not going to occupy much screen space. So in that case, affix a little ampersand at the end, which was an indication to the cell to start this thing immediately in the background, so you don't have to do the whole like suspend and then background it yourself. You can see what's reported is the process ID listed over here, and then the yes command that's running in the background is as well. You can see the processor time that it's occupying ticking up gradually, and this other yes sitting here still in the suspended state. I could put that one in the background as well. There's background, let's see if I remember right, I have that's number background, that job of number 1. Oops, sorry, let's see. Whoops. Well, let's see. I'm not sure what I did now. So, and there's let's see. Let's just kill these guys. How's that? I'll get myself a top up. Pressing the K command in top will allow you to kill things, and for instance, in this case, I want to get rid of 6878, 78, and that to get rid of that guy, and then we're going to kill 10588, which I somehow managed to get into the foreground unnecessarily. Okay, so we're back. Good. So good for recovery in that respect. Really common thing to do is fire up top, see what's eating up CPU, and attempt to kill it by issuing a kill directive on that. So got myself into trouble there, but getting out of trouble is an important skill. So glad we had a chance to sort of work through that together. To that end, learn a little bit about this foregrounding, backgrounding business, as it can be extremely useful if all you have is a remote login to some server. It will allow you to do potentially multiple things at once in the same terminal without the need to log in more than once. So we've talked then about this kill command as a way to issue a sort of a signal that will go to a process, and then potentially some keystrokes also, that if you have a foreground process that's running in a terminal that will manipulate it in various ways. Control C and Control Z will either send an interrupt signal, which often kills a process, though not necessarily, or Control Z, which will suspend a process, putting it to sleep and making sure that it won't resume until later on. We've seen that yes is an easy command to suspend and to kill with Control C. A slightly harder program to kill is one that we've demonstrated before. It's this no interrupts guy. And when we get to talking about signals, you'll see that this is harder to kill on account of it catches most common signals that would normally kill a program and handles them by ignoring them. So to that end, in this directory, O3 process basics, if you gcc that no interrupts fellow, to start typing it, its basic loop is to print something to the screen, go to sleep for a while, and then print something to the screen again and go to sleep for a while. The common command to kill, if it's in a foreground process, Control C, will send an interrupt signal, but this program will catch that and ignore it. So it's not possible to get rid of this thing with a Control C. You have to pull out these bigger guns in that respect. So a kill -9, except I don't know the process number. I could look it up, but for instance with pgrep, we'll search for a process named a.out. That gives you a number. But there's also a pkill that will allow me to say kill any running a.out by sending it the default signal, which is a terminate signal. The trouble with this is that there's a nice way to shut down via this sig term, but that's a signal that processes can ignore as well. So at this point, I need to be fairly insistent to send the -9 or -kill signal. That's a signal that every process will respond to with death. The other one that's possible to use in this case, if I rerun a.out, is Control-Z sends the sleep signal, or suspend signal, as it were. So there's no way for a process to ignore that one. If I press Control-Z now, this thing is suspended. I can bring it back into the foreground, and it's running. Similarly here, let's see, it'll be, let's see, sleep, I think, or is it, sorry, maybe it's suspend. Shoot, I can't remember. Okay, let's see. So, look up man for this thing. Let's see, blah, blah, blah. Okay, need the command that lists all of the known signals. What is killed? Crap. Well, I can't remember right now. I'll look it up later, but there is a way in terms of signals to send the sleep signal from a p kill. Hang on a second. This will be man kill. I'm looking for. Let's see. List. Okay. Print list of signal names. I killed lists. And I'm looking for quit, kill, trap, sig kill, ill, sig bus, sig v. Looking for something that has to do with stop 20. Stop. Okay. So ostensibly then p kill stop. Do it. Okay, there it is. Okay, that's what I was looking for. So the names for these things vacillate from one context to the next. Just be aware then that. You can see this is an interruptible sleep, so we'll actually get that signal and say no. What I need. Oh, I woke up actually. That's right. Issuing a signal will actually wake something up from suspension. I'll get rid of that guy for now. So at any rate, we'll talk much more about signals later on. Just be familiar then with ways to get rid of misbehaving processes, at least the ones that you own. As we discussed in lecture, processes are owned by a specific user, and if you don't own the process, chances are likely that you will not have permissions to end it or otherwise manipulate it. So we've talked now at length about sort of job control, and it would be worthwhile to go through a process on your own to compile this thing, to run Invincible, to do various things to end that program. Good review here of the -o option GCC to compile this program to Invincible, as it were, and then to maybe play around a little bit in terminal using VI and suspending it, making something and then firing back up, sort of reviewing or sort of coming back into the terminal and remaking a common sort of editing cycle. This is an optional exercise, but is worthwhile because it relates directly to how you would typically go through work on a project on a day-to-day basis. We'll close down this discussion of process states just by mentioning that the context switching associated with going from one process to the next, to identifying that this process should go to an uninterruptible sleep because it's waiting for some I/O to happen or something like that. This has to do with operating system internals that are related to system calls. So this next state diagram deals with the interaction with the operating system itself and how it will potentially deal with moving processes from running to in the ready queue to be run later, or waiting for some I/O to happen. So typically a running user process will either make a system call, which will require the operating system act on its behalf, moving to state 2 here, or the epoch of time associated with that running process will expire, and a hardware signal will trip the operating system to run some code associated with it. Now, if it's an immediate sort of return from a system calls and something can be done fast, then the user may get control back immediately. Otherwise, for instance, if time expires, the operating system may mark this process as, okay, your turn is done, we're going to put you to sleep right now, and eventually you get woken up and ready to run and get scheduled again. Or potentially this sleep also might have to do with I/O completion, in which case it'll be in the sleep state, state, and we'll move back over to the ready to run part. It's the business of the scheduler, part of the operating system, that when it's in operation will look at the available processes and attempt to exact some sort of fairness in terms of who gets to run and for how long. There are priorities associated with processes. For instance, long-running daemons, background processes that are owned by the operating system may actually have lower priority than user processes, or higher priority of user processes. So there are a set of commands that can adjust process priority, but we'll probably not touch on them. The idea of a context switch, of changing from one program running and having the CPU to another program running and having the CPU, is central to this business, and it only happens while the operating system has control. And that can be gotten either via a system call or some sort of an interrupt that will move a running program away from its instruction set and into the operating system realm. The next bit that we are going to talk about is a brief review of the kinds of memory that are available in C programs. Take just a moment and recall, if you can, the four main areas of any running program that are sort of present in memory at any given time. This isn't specific to C, but it's often talked about with respect to C because it's fairly transparent, those four parts. And if you can, give a brief example of how you would declare in a C program some sort of variables or values that will reside in each of those four different parts of memory. All right, if you're done with sort of checking on that exercise, the answers show up on the next slide. Generally, we'll talk about the four areas of memory as the stack, the heap, the global area of memory, and the text area of memory. And if you're looking for examples of what goes where, any variable in a C program that's declared outside of the scope of a function will end up in that global area of memory. We'll see in a second a diagram of where that resides. Things that are local to a function, for instance parameters or local variables, those will go on the function call stack. So during the run of the programs given here, we'll start execution in main, and there'll be an area of memory on the function call stack for each of the local variables, x, c, and p here. As this func guy is called, a new stack frame will be opened up for the parameter a and the local b. That goes away at the point that that function finishes. Just as main finishes, these variables are automatically recouped by popping off of the stack. The other area of memory that's pertinent to manipulation is the heap. And this is the sole purvey of malloc and free. So when I ask malloc, please find me memory that's big enough for a single integer, what I'll get is a pointer into heap memory that will occupy the cell of memory associated with P, but will point at a different spot entirely. I can manipulate that through, for instance, a dereference of P to set it to be 10 here, and deallocate that heap memory via a call to free. These are explicit asks and letting go of memory. Those are pertinent to all C programs that have to have some sort of dynamic behavior. And all of this program code that actually makes assignments, calls functions, and changes values, that will be in the fourth area of memory, the text area, which corresponds to assembly level instructions for changing variables, calling functions, popping off the stack as you would finish a function, and to some extent system calls that we'll get into later. A reasonable picture of this comes out of one of your optional textbooks, Robbins and Robbins. Typically, an area of memory associated with a running process has the following stuff associated with it. The stack lives in high address memories and builds downwards. So as you would call a function, if your stack pointer is at 1024, then the new stack frame for the function that's being called will be at a lower address, 900 for instance. Versus the heap will usually start at a low memory address, and as things are allocated, grow forwards. The stack usually has some operating system bound associated with it, so it's not possible to continually call functions. Eventually it will collide with the address space of the heap after many iterations, and that usually happens associated with a misbehaving recursive function, thus the idiom stack overflow problem. But the global data will show up in two sections lower down in memory, uninitialized or initialized data, and the assembly instructions for program text are down here. The high addressed stuff usually has to do with two things we'll talk about shortly, command line arguments and environment variables. And C exposes these through the argc and argv arguments that come into a main function. We'll see that that pertains to the command line arguments. Environment variables have a slightly different mechanism to access them. A somewhat more detailed picture comes from Wolf Holzman, a computer scientist who stitched together this very detailed image of what's available in your typical running process. Now, things that we'll eventually talk about in here, certainly there's a mention up here of environment variables, and then the argv, argc stuff, potentially stack that will grow down eventually into heap. Interestingly, there's a middle area here associated with shared memory, usually dynamically linked libraries that we'll talk about later on in the course. Heap down here, which is governed by malloc again. An area of memory associated with initialized and uninitialized global variables. And interestingly, there's even a mention here of a fixed string like a printf format %d. This is actually stored in the initialized area, usually as a string table. And if you look carefully at the executable file format favored by Linux, ELF, you'll see specific mention of string tables that contain things like %ds. And finally then text down here that may comprise code for specific functions that you've written, or code for something, a library that you didn't write but statically linked against this. And finally, way down at the bottom, there's actually code associated with the C runtime that is important to get the program started up. And this is usually the stuff that happens before main is ever invoked to get, for instance, the environment set up right. So it's worthwhile to review some of this, but most of this is business that should have been covered in a machine architecture class such as CSI 2021. So review there if you need more insight. At the operating system level, you would look at the working RAM associated with memory and see something that looks along the following lines. That each process is its own little world. Within here, there's a stack and a heap and a global area memory and linked libraries and so forth. But then a second process has a different stack, heap, global area memory, and text for its assembly instructions, which are different. Third process down here has the same sorts of stuff, and the operating system itself, probably at a low address, has some space reserved, although it varies from system to system whether the operating system reserve stuff at the high end or at the low end of physical RAM. Now, this is a high-level picture. It's abstract, and it is certainly wrong in many respects. We'll discuss some of the ways it's wrong later on when we cover virtual memory in the middle of the class. But this image should also bother you to some extent in terms of two facets that will need later explanation. The first is if there's a process sort of layout like this, for instance, process 2 sandwiched in between process 3 and process 1. It's not clear at all, as you would allocate heap memory, how things would work out. For instance, if I wanted to keep allocating heap memory and got to 1 or 2 or 4 gigabytes for process 2, you would either, if you're growing the heap at the low end, bump up against process 1, or at the high end against process 3. So that'll need resolution, and the resolution will have to do with paging. It should also be slightly bothersome that these addresses at which things are at are not the same, as in process 3 starts at 4200, and you might wonder about behavior as to whether it will behave differently if it starts up here where process 1 was at. Virtual memory is also going to be the answer for that. The other part that's bothersome is how system calls could be implemented if this was our only abstraction. For example, as process 3 would make a system call, that's a function call, and the operating system functions needs a stack to operate on as well, and so it becomes a question, do you put that stack in process 3's memory area, or do you put it somewhere else? If you put it in process 3's memory area, there's the real danger that the user process could manipulate variables that the operating system is using. And that could allow for sort of circumvention of some of the security mechanisms that the operating system would typically have. For example, you make a request to remove some file within this process. Since the stack is for the operating system is in process 3's memory area, you by hook or crook have process 3 actually change what file is being removed so that the operating system removes something else that you wouldn't normally be able to get to. Now that's resolved fairly simply by ensuring that each process has its own area in the operating system that will function as the system call stack. So as process 3 would make a system call, there's actually an area in the operating system protected memory that is associated with process 3 and the system calls that it's running. Since process 3 it does not have permission to reach inside and touch memory that's up here that belongs to the operating system, that will preserve the security facets there. And similarly, I should mention that process 3 cannot reach into the memory of process 2 or process 1. The operating system will enforce boundaries, and attempting to do so for process 3 will get a segmentation violation. As in, if it tries to go into process 2 and change variables there, then the operating system will usually kill the process. The next sort of step in getting geared up to start, for instance, working on the first project, which should be posted shortly, is to reacquaint yourself with all the problems that you have in C programming that aren't necessarily problems in other programming environments. A lot of this has to do with the ability of C to manipulate memory directly and according to the conventions of machines, as in there aren't too many limits put on you. Now that doesn't mean you can't hurt yourself. We've already mentioned and alluded to the fact that if you go out of bounds in terms of the memory area of a given program, the operating system will usually kill the program. There are a whole host of other problems, though, that the operating system just lets go. For example, it's highly possible to bum around in the stack and clobber variables or reference variables that don't have meanings. As in, within the memory area of a function, there's this stack. You can go below where you really should be or above where you should be through pointer arithmetic, for instance. I mentioned segmentation faults, attempting to dereference null pointers that point nowhere, a zero pointer as it were, usually is out of bounds and will lead to a segmentation fault. It's possible in C to use uninitialized variables because the compiler doesn't actually give any guarantees that variables are initialized unless you do it. And it's also possible to have memory leaks. For instance, you keep mallocing stuff but never free it or lose pointers to malloc stuff, in which case it's not possible to free it. One interesting example of stack problems comes from the proprietary program overflow.c. We're going to have a quick look at this thing because it's worth looking at. I'll use the less pager for that. So this is overflow.c. This isn't Stack Overflow, as you might think. Instead, this has to do with, well, I say Stack Overflow in the sense of growing the stack too much. But it is overflow the area of the stack that I'm looking at. So, for example, I'm going to lay out here a short array. There are 3 characters in A. They are A, B, and C. I'll give myself a little counter and then start up a loop that will run forever. All this loop does is print the contents of A. Now the first 3 things in A are well defined, that's A, B, and C. But since I just keep on chugging along, printing things out, every 40 characters or so printing a new line, this is going to walk right off the end of the array into higher addresses. So usually an array is laid out as if character A is at memory address 1024. Characters are 1 byte big in C, so now B will be at 1025, C at 1026. But then I start getting into parts that are less well defined. At 1027, it's not clear what's going to be printed. So we will see. You can see on compiling this thing, overflow.c, that the compiler has no particular complaint of this, and it is an illustration of the limits that the compiler has in terms of checking safety. As I will run this thing, a.out, I eventually get a segmentation fault. and that's on account of I get to a spot where I just do not have access to that memory anymore according to the operating system boundaries, and so it will kill my program. Interestingly, there's a bunch of stuff that potentially makes sense here. So scrolling way back up to here, I'll see that ABC and then a bunch of gobbledygook. And most of this is binary stuff that my terminal is trying to interpret as characters but is having a hard time with, although it's having some success in that, oh, this is an O with an umlaut. Well, it's probably not meant to be that. It's just some bit string that can be interpreted that way. At least there's an x86-64. That seems fairly obvious. But up here then are a bunch of interesting looking things like shell and Phaedrus and temp and closure home and cinnamon and Java 8. So a bunch of other stuff that's semi-interesting in that respect, along with other stuff that's sort of listed on here like home Kaufman. At least that's interpretable before I run out of stuff to do. One other quick thing you can do, which is semi-interesting in this respect, say hello, goodbye, and adios up here. I'll run this thing again, and it should be the case that, okay, here's all the stuff I mentioned here, and there's my hello, goodbye, and adios mentioned up here. The insight that you should have here is that this stuff, which is stored at high memory addresses compared to where the array is at, was actually mentioned earlier on in terms of the typical layout of a running C program, that the argc, argv, and the environment variables are stored up here above where main gets its initial sort of run at things. So what we're seeing is both those command line arguments stored someplace and the environment variable stored someplace. So it's worthwhile now to talk about those two things as a mechanism. Now, I'll just mention quickly that you'll have to deal with all these problems that C has, and it's worthwhile to get some support from this. You won't be an option to not program in C in 4061. That'll be our business. But out there in the working world, this is why folks program in Java or in Python to avoid many of the problems that we're seeing with C here, and that it does weird things and allows for a lot of flexibility, but that can get you in trouble. You'll want to acquaint yourself with tools like Valgrind, which are free on Linux and Mac. It's an excellent memory checker, which, as you would make use of the programs that are sort of compiled in C, you can ask Valgrind to do a memory analysis of that. Go through the exercise that's associated with this if you're unfamiliar with Valgrind as a way to sort of check memory. It will be an invaluable skill and help as you are working on your assignments. And know, too, that most of the assignments that we'll do in here will have automated tests that include checks with Valgrind to ensure that memory is both allocated and freed correctly, and that you aren't going out of bounds any place that would potentially cause problems. You may also want to acquaint yourself with debuggers. GDB is the most common one associated with debugging C programs. It will save you from having to put innumerable print lines in various spots of the program to try and figure out what's going on. We may review this briefly, but it's also presumed that you have some experience with this based on your previous classwork. So this business of command line arguments and environment variables has to do with communicating information to a program at startup mainly. And it's often the case that you would want to do this, for instance, to inform a program, read or write to a specific file, iterate for some number of times, print more verbose or less verbose output, or potentially issue some piece of information that asks the program to report immediately or shut down, although these latter two are more the purvey of, for instance, a signal to say shut down or tell me what you're doing right now. We'll talk briefly about these first two, command line arguments and environment variables, and discuss some of these later mechanisms like I/O libraries and signals later on in the course. It should be familiar to you, this idea of command line arguments, that in a C program, there are two optional arguments to main. They are argc, which is how many command line arguments are given, and argv, which is a an array of strings or array of character pointers, as it were, which are those command line arguments. So for example, if I were to compile this print13 program, which, as you can see here, prints out the first and the third command line arguments, the image that I might get would look something like is over here in memory, although there's one minor difference that we'll get to in a second, and that if I pass along the command line a -C, and then the number 10, and then the number 2.0, over here in that argv array, I would see the first pointer points to a -C, that's null terminated. That comes from this first command line argument. A 10 that is associated with the second command line argument, that's 10, and the 2.0 over here. Notice that these are all strings, so if I wanted numeric values associated with them, I would have to do a conversion of the string 10 to the number integer 10, or the string 2.0 to the number 2.0 in floating point format. That is not done automatically. Typically, argv is ended with a null, as in this is a pointer to no place, but it's usually best practice to honor argc, which is how many of these arguments are specified. So in this case, there are actually 4 things on the command line. That includes the program name over here, a.out, which I should mention now is mislabeled over here, mine. So to that end, indices 0 through 3 are given here. Now, it's a little bit questionable, like, why would you have the command that's given in here as one of the command line arguments? This is an old Unix convention that would actually allow you to write one program and then make copies or links to it with different names, which could then be detected at runtime, and based on the name, the program might behave differently. This isn't done a tremendous amount anymore, but there are example programs that are out there that will potentially do this, that specifically relate to, for instance, low-level systems programming. We may touch on some of those later in the class, but I don't have any at my disposal right now, so we'll pass on that. For the moment, though, a good exercise is to write a quick C program that would print out all elements of this argv array. You can see an example of the kind of thing that you'd have to do in there, for instance, with this printf %s, substitute a string in here, and argv1, that'll print out the first one, and the third argument down here. Now, I think it's worthwhile also to mention quickly that this program is dangerous in that it unequivocally prints out the first and third arguments irrespective of whether they're there. So if I bop down here and compile that thing, print13.c, and I run this thing, let's see, hello, goodbye, and aloha. Then you'll see aloha and hello on the screen. That's the first and third. If I leave off aloha, I'll probably get a segmentation fault because I'm attempting to dereference some element of the array, that third element of the array that isn't actually there. It's in fact the null that's mentioned here. And if I leave off arguments entirely, I'll probably just get a straight up segmentation fault. So more typically, and this is what you'd have to do in this print all arguments bit of code, is that you would use argc in a loop to either loop through those arguments and only go up to the number that's specified validly. It's a business of the operating system as it starts its programming up running to set things up so they look like this, to populate argc with the right number, and to populate this argv array with the contents that are coming from the command line. We'll actually see how this is done later on in the class. But for the moment, take a second and crank out a quick C program that will do that. By now you should have finished up that C program that prints out all arguments, and it should look something like this. And if you got stuck, you can draw on print args that comes in here in the code pack that solves this problem. And in this case, I just printed out how many things are going to come in argc. I have a little loop that loops from 0 up to argc, but not including it because that would be out of bounds. And then here, print out the argument number and what's at that position in the argv array. Pretty elementary C program. What gets more interesting is trying to process those command line arguments to, for instance, populate variables like I'm looking for an input file and it's named on the command line, or I'm looking for a sequence of options that can change the behavior of my program. The other main mechanism to communicate information to a program immediately is through environment variables. As you are running a shell, it has an environment that can be checked and manipulated, and this can actually have interesting behavior changes within the shell itself. For example, you can check environment variables within a shell by echoing the name of the environment variable prefixed by a $sign. Echo is a command that will print things on the screen, like echo hello. Preceding something with a $sign means don't print for instance, it can echo path on there. There is a path environment variable. If you prefix this with a $, it says not the word path, but the value of the variable path. So this will print out something somewhat more elaborate, or for instance, my PS1. That corresponds to the format of the prompt associated with the shells. So for instance, if I change this, here's PS1 equals just the let's see, prompt, and I'll put a little caret here with a space. Then you can see this changes the behavior of the shell, so I actually see something different at this point. Now I don't like my prompt looking like that, so I'm actually going to type, this is a command that I wrote to just reload my configuration file so I get my prompt back. But there are a variety of other environment variables that are often honored by programs. For instance, another common one is pager. I have mine set to less, so that if I say, for instance, look up in a manual, man GCC, this pager variable contains what I want manual page entries to be displayed as. So in here, I'm actually running the program less right now to be able to look at this. Quick throwback, I could suspend this with Control Z, and if I look at the jobs I have, I still got those two old VIs there, and also then this man, and if I want to do something with GCC, blah, 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 I can actually then recall that man page here to continue right where I left off on that. But we were more interested in pagers at this point. So if I change my pager to be, let's see, cat, for instance. And cat is a program that just spits things onto the screen. For instance, print13.c, that goes onto the screen. Now when I would launch man for GCC, I would just see the entire man page splayed onto the screen. Not particularly useful, so I'm going to reload my configuration right now, which gets me back to a pager of less instead. So to that end, there are lots of interesting tricks and configurations that you can explore on your own. The way that programs usually see this is then that the operating system provides an environment of name, value, correspondence. And typically environment variables are all caps to sort of distinguish them. You can see the entire environment in a shell by typing env, and this will list on each line name associated with a value. Important ones on here, you can see options that I use to less. You can see my favorite editor has to do with Emacs. You can see my home directory is listed here, that there's a display because I'm in graphical, to some extent where my mail is at, and a bunch of other things on here, including my username. These are all variables that any program that is launched from the shell will inherit, and so are therefore a way to get some information from the outside world, which can change how that program behaves. C exposes this via place in memory that's devoted to environment variables, and we've seen then that there is a spot, it's higher up in memory than the command line arguments or even the stack frame for main, that's devoted to those. They'll have a structure that's similar to this, and that there's a global ** environment variable, environment pointer that points to an array of pointers to this. But it's much easier than directly accessing this thing to make use of a set of standard C function calls to access environment variables and look them up by name. Interestingly then, this is just an array of pointers to spots that are probably someplace in memory, with things like home and path and shell, where this is all one string that's null terminated. So to that end, familiarize yourself, if you're going to work with environment variables, with the get environment, set environment, unset, and put environment commands. We'll focus our attention on these first two. Get environment just asks for the name of an environment variable, and if it's defined, will return a pointer to the string representing the value associated with it. Or if there is no environment variable that's set according to that, it will return null. Set environment, on the other hand, will take a name and a value and set the environment so that it's associated with that. Now, interesting that it takes one additional option that will dictate the behavior of whether this exists or does not exist, how to behave. So the example here, if rewrite's non-zero, then an existing definition for game is first removed, or if rewrite's 0, then an existing definition isn't removed. Then it's set to the new value, and this can actually result in an error potentially. So take care that you use appropriate calls here using that rewrite option as needed. A good exercise to sort of work through on this, to make use of these two new functions to get environment variables and set environment variables, is to write a tiny little C program that I called Environment Vars that does the following two things. It will look for the two environment variables rock and volume and change its behavior based on that. In the event that both these are unset, and note here the shell command unset will get rid of any definition associated with those two, the named environment variable. I'd run a.out and the program would simply report that both these things are not set. I'll export the definition of volume equals 7, and that guarantees then any sub-processes, any programs that are run from this shell will be able to see that definition. Rerunning the same program without recompilation at this point will actually report what the volume is. It's set to 7 right now. And if I export this rock variable to be yes, running a.out at this point will actually change volume to 11. It was 7. It's being changed here to 11 and then printed out at the end of the day. If I echo back in my shell what the volume is at this point, the shell sees 7, and that's on account of a child process here. A.out cannot actually change the value of an environment variable for its parent. That's a change that only the child process will see in its own environment. And this is typically accomplished by a parent will copy its environment into the child so it's distinct, and the child makes changes will only see that locally. So take a second, attempt to crank out this program. It'll just be a series of if-then-elses. Make sure to check carefully with your get environment what the result is, noting that null will indicate that something is not set versus a non-null will say that it is set and has a value. All right. Hopefully you've gotten done there and made use of this rewrite option to overwrite any previous definitions for something that's there. If you're looking for more guidance on this, the solution that I concocted is in environmentvars.c, and if you track through this thing, you will see something about a variable attempting to sort of get an environment variable rock, and if that ends up being null, then I'll just print out what that rock is not set. If it is null, then I can fall into this case which deals with a rock sort of being something, and so I'll print that thing out. This should dictate then a change of volume from whatever it was to 11. Note the 1 here for rewrite, and that if volume is present, I'll want to actually overwrite whatever its definition was with this new definition, versus with a 0 here, that may actually cause a failure if it's already defined. The fail here will indicate could not change, but I don't see there being any real way for that to happen in this case. Finally, after sort of changing it, I'll do a check to see if volume's there. If it wasn't there, but rock was set, it will certainly be there after doing the set environment. But if rock wasn't set and I get to this stage, I'll just be looking, did the environment sort of push anything else out. So I'll change this little volume guy to be not set and print that out, versus if I get an actual value for that via volume, that's what gets printed here, for instance 7 in that case. So make sure you understand the basics of how to at least access some environment variables. This will be part of the assignment 1 code that you'll have to write, that you change your program in that case to behave slightly differently based on some environment variables. But that's all I've got for you for the moment. We'll pick up next time with a discussion of how to actually start launching processes using the fork command, and how to wait to see what the results of those processes finishing are using the wait command. These are C-level calls, but more on that later. See you next time.